Hi, Physics 20. Today I'm going to tell you about a couple of types of friction, static and kinetic, and we'll do a couple of examples that'll help you with the assignment. All right, so you may have noticed when moving a heavy object that the most force is required when you start its motion, and once it starts moving, you can usually ease up. All right, it takes less force to keep it going than it did to start it. Part of the reason for this phenomenon is that for every object and surface, there are two types of friction. Static friction prevents it from moving in the first place, and kinetic friction resists an already moving object. Okay? It's right there in the name. Static means not moving, kinetic means moving. And the coefficient for static friction is always greater than the coefficient for kinetic friction when we're talking about the same object and surface. Okay? And the coefficient is related to how much friction there is, so higher coefficient, more friction. So what this is saying here is that for any object and surface, static friction is greater than kinetic friction. So it takes more force to start something moving than it does to keep something moving. Now I just want to run through a couple of examples. So for rubber on asphalt, like for a vehicle driving, the coefficient of static friction would be 0.6 and kinetic would be 0.5. All right, this is a good example. You'll see a couple like it on your assignment. So I've got a vehicle, it's moving 20 meters per second, and the driver slams on the brakes. We're going to determine the vehicle's stopping distance and acceleration. I think we'll actually find the acceleration first. Okay, I'm going to sketch a really simple free body diagram to help us figure out what's going on here. So that's my vehicle. Looks amazing. Okay, the force is acting on this guy. There's going to be Fg straight down and a normal force straight up. I'm going to be saying it was driving to the left. All right, now once it slams on its brakes, friction between the tires and the road work to slow down the vehicle. And what I think is confusing, and I'm going to try to convince you, is there's no more force moving it forward, because when you slam on the brakes, you take your foot off the gas pedal. Okay? So the engine is no longer pushing the vehicle forward when you slam on the brakes. That wouldn't be a good idea if you're trying to stop. So what we have to recognize is that friction is going to be the net force here. There's nothing working against friction when you're trying to slow down. These other two forces, the vertical ones, they just add up to zero, because clearly this vehicle isn't going to accelerate up or tunnel to the center of the earth. It's going to slow down. All right? So we can find the force of friction, and from there use Newton's second law to find the acceleration. Okay. One question would be, do we use static or kinetic? Well, this vehicle's moving. It's moving 20 meters per second, so we're definitely going to use kinetic. All right, which I've written up there as 0.50. Something we discussed that now becomes important is that the normal force and the gravitational force add up to zero. That means that their magnitudes are the same. So let me write it like this. It's just the coefficient times the gravitational force, which is mg. Okay, I do that calculation, I get 7,358 newtons. All right, so that's the force of friction that's slowing this vehicle down. But we also described, and our free body diagram kind of tells us that that is the net force. Right, because you are no longer, or the driver is no longer applying the gas pedal. There's no force propelling the vehicle forward. It's just using what you might describe as its inertia. It was already going a certain speed. that doesn't just disappear at once. We need to accelerate it in the opposite direction to make it slow down. All right? And this is logically consistent. I mean, to accelerate something in the opposite direction, you need a net force in the opposite direction, which we just calculated. Divide by the mass, and we will get the acceleration. Okay. So the way that my page is set up is that would be acceleration to the right and its initial velocities to the left. The good news is I don't think that's going to matter too much once we set up our kinematics. When we're finding the stopping distance, well, we know that VI is 20 meters per second. We know that the acceleration is 4.905. And VF has got to be 0 if you're going to stop. We're looking for a D. We're going to use this guy here. Okay, and I'll just continue along the same kind of path I was already on. Okay, so I actually get negative 40.8, but just a reminder, using this formula, a negative just means it's in the opposite direction as the acceleration, which makes sense. The acceleration, in our case, is slowing us down. The way I've drawn it is to the right, but we'll definitely skid to the left as we come to a stop. Okay, so this was a nice example, used our new stuff. Newton's second law gave us an acceleration, and then just a simple kinematics application there, which we are all experts at. Okay, I got one more example I want to run through, and it's like a really standard one. We were doing things just like it before. Now we've added static and kinetic friction, and you'll see what that means for our calculations here. So I've got a box on an incline, static coefficient's 0.75, kinetic's always less, in this case it's 0.6. I put a question like this on the unit test and final exam every single year. So does the box slide? If so, calculate its acceleration. Well, let's start with a really, really familiar box on incline free body diagram. Okay, so I've taken care of the gravitational force there. And as you're aware, we get a normal force, and we get friction up the ramp like this. So nothing's changed so far. The only thing that's going to be different is there will be two values for friction, and we have to know when each of them is relevant. Okay? We've done problems like this before where we compare the parallel force to friction to see if it slides, and that's exactly what we're going to do here. All right, so actually what I think I'll do is sneak my parallel force over here because I know I'm going to need it. So it's always mg sine. All right, so we have that 37.6 newtons of force is trying to pull the box down the ramp. If that's greater than static friction, this thing's going down. Okay, I'm going to write that out because it's always going to be true in a question like this. If the parallel force is greater than static friction, the box will slide. Okay, so let's calculate static friction. Write it as static FF. So I've got it, it's the static coefficient multiplied by the normal force. There are no additional forces when you just put a box on an incline, so the normal force will be equal to the perpendicular force here, which never changes its mg cosine. All right, so just be careful here. You definitely use your static coefficient, and then everything else should kind of just flow. I did that calculation and I got 23.6 newtons. Compare these guys. That means this box is going to slide. The fact that it's sliding means that kinetic friction takes over. And that's actually going to be the force of friction acting on the box as it accelerates down. All right, so we do have to do that calculation now. But the good news is it's identical to our previous one, just with a different coefficient. So I'll move through this fairly quickly. All right. Hey, we're almost done, people. Now we just got a typical box on incline friction question we were already doing. We just got to subtract this friction from the parallel force bringing it down. So the net force is going to be parallel minus friction. And just a reminder, we're using kinetic friction because we verified the box is sliding down the ramp. Since it's sliding, we know that we have to use kinetic friction. That's for moving objects. Okay, so I get 18.7 newtons as my net force. Okay, and as we've done 100 times, just hit it with Newton's second law and we'll be done. So the mass was 5. All right, looks good. I hope it helps.